All right, we are going to look at an example LAMP script that I wrote. This script is used to benchmark the TIP4P-Ew water model, and the script is going to have the following main sections, which are just going to be like initialization, data acquisition, and actually running the simulation itself. So I'm really just going to go kind of like line by line. I'm going to go line by line for the most part as to what the major points of the script actually are. So starting right at the very beginning right here, we have the clear function. So if I ran a simulation beforehand, I'm going to kind of clear the screen, the space of everything that I did beforehand. So I'm just going to be starting brand new fresh every time I run this script, echoing both. That is going to reproduce because how I run the simulation is going to be from a terminal program, and when I run the simulation, I want to be able to actually see what the program is actually doing itself. So I want to be able to duplicate that output onto the terminal screen, so I can actually understand and see what's going on. So in case something breaks down, in case I have an error code and I just stop, I can make it a lot easier for troubleshooting as well. Units, again, there's a list of those on the LAMMPS website as well, but the main units I'm just going to use right now are going to be the real style. Atom style is going to be full. Boundary conditions, PPP, that stands for periodic in all three coordinate directions. So that's what's going to allow us to get away with simulating a small amount of water molecules, about 512, and reproduce them infinitely in all directions. Dimensions, yes, three-dimensional simulation. You can also run 2 dimensions, but this simulation is just going to be for 3 dimensions as well. So now that I have that kind of out the way, now we're going to start with the entire where I'm actually going to put the molecules after the simulation. So the region command. So I got the command region. I'm going to call it domain, and the type of a region I'm going to be utilizing is a block. So for the block domain, it's going to be a rectangular prism, and this is x min, x high, x min, x max, y min, y max, and z min, z max. You can see it's just a simple cube that has has an edge length of 24.8 angstroms, and the units I'm going to be utilizing are going to be that of the box. So in the units that we're utilizing in this particular script, it's going to be angstroms. So this is in 24.8 angstrom size box. Creating the initial system geometry. Now I'm going to need to create the box itself. So create box command. 2, I'm going to allow for 2 types of atoms in the simulation. So since I'm utilizing water is only composed of 2 different types of atoms. I have oxygen atoms and I have hydrogen atoms. So I need to allow the simulation domain to account for both of those. Bond types, I'm only going to have 1 bond type between the oxygen and the hydrogen. Extra bonds per atom. I need to allow for a maximum of 2 bonds per atom, which is going to be the oxygen, because the oxygen is going to be bound to 2 hydrogen atoms. And for extra angles per atom, I'm only going to have 1 angle side because I only have 1 type of a molecule in the simulation, which is water. Again, I only need to allow for 1 of those in the entire simulation domain. Read data. This file right here that I'm going to highlight right now, this is the name of the file that actually has the location of all the water molecules. That will be in a separate video as to how did I create these water molecules in the first place, and how I'm going to add them into the simulation domain. I'm going to just append their molecule ID, their atom IDs, because this is going to be useful if I was doing a let's say an explosive boiling run where I had a gold substrate in there. Those atoms would already have IDs to them. So instead of running the risk of having atom IDs already appended to these water molecules and having multiple atoms that share the same exact ID, which would cause the simulation to crash, I'm just going to append them where that, all right, if I had 1,000 gold atoms, then the first water molecule in this in the TIP4P water model file itself is just going to be, okay, it's going to be atom number 1001. So that we go from there. Setting the atomic interactions and attributes. So again, a lot of this stuff is going to be, there are plenty of ways of running this simulation. There are plenty of ways of doing this, and you can actually possibly have this data into the the file that I read the water molecules from. But again, this is not the most optimal. This possibly isn't the most optimal way of doing it, but this is the way that I know for a fact works. So I'm going to call mass 1 is going to be the mass of hydrogen atoms, and again, this is the it's molar mass right here. Mass 2 is going to be the oxygen atoms, and here's the molar mass right there. The pair style, that's going to actually control the interaction between each water molecule. Again, if I can just flip to the, let's see if I can go to the screen right here, just kind of see if I can find the, where is it? Ooh, let me kind of get rid of this. Yes, here I have like, the TIP4P-Ew water model that I'm simulating right now. You can see like, the parasite that's supposed to use for this particular type is down here, which is what I have in the script that I have itself. And if I just kind of scroll down briefly, you can see all the different parameters that go into making a particular model of water molecules, of water styles. But again, that's going to be like, for the particular model to try to benchmark. So let me just flip back here. Again. So yes, I have this all set up. Those are parameters that you can find from like whatever thing you're trying to benchmark. Yes, and the purpose of this, like, the script itself is to benchmark to something that already exists. And the point of that is to like, make sure like if I'm benchmarking between to like, another research paper or to the like, a steam table of like the thermophysical properties of water itself, that makes you let you know that, all right, I'm doing a good job as to recreating the water model so that when I try to do something different, like perhaps like, add an electric field or like have it in a different type of style or configuration, I can be confident that any differences that I'm seeing aren't attributed to like, an error and be like, initializing the water model that I'm trying to utilize. So from down here, I got the water pair coefficients that I have, like, you can see between each water model as well. You can see that if we like, get a little bit more complex, they're going to have more interactions between the two. I need to define the interactions between the oxygens to each other, the hydrogens to each other, and the oxygen and hydrogen to each other. But you can see that from here that the only interaction that's important in this particular model is the interaction between the oxygen atoms in two different water molecules. Again, right here, since I'm utilizing a long-range style for this because the electric portion, because each of these atoms has a charge associated to it, and electric charges like, act at a distance infinitely. So I need to have a way as to like, accounting for that. And this is the particular style that I'm utilizing, and the accuracy associated with that is like 1 times 10 to the negative 6. That's, you can change this value to like, I think the default might be to the negative 4th, but it will cause the simulation to run a little bit faster, but that comes at the expense of it taking like, the simulation will run a little bit faster, but that comes at the expense of it being less accurate. So what if I have it back up to 10 to the negative 6? Okay, now I'm not running I'm going to be a little bit more accurate, but it's going to take a little bit longer to run. So you need to figure out like, what is the trade-off between like, your simulation, how important is accuracy to you. Bond style that I have right here, that's it's a simple harmonic spring. There are different types of styles that you can look at too in the LAMMPS documentation, but that's not important for this. Bond coefficient, all right, I've got like, for bond 1, I'm going to have like, rather stiff spring right here with the bond length that is given by, I think, 0.597 angstroms. And some of the comments that I have here aren't going to match up exactly to what I have on here because I actually had utilized the script for something else. So yeah, the point is like, once you have the bare bones of a script for like, one type of simulation for like, water benchmarking, it'll pretty much be the same for whatever else you're doing. So it's like, very modular. The only issue is like, having that first script set up so that you can kind of like, repeat that as you go forward and go along. So pretty much kind of the similar thing with this angle style. Again, it's a harmonic bond for that as well. I need to make sure that like, the angle matches up to what I had in the documentation before, and that can kind of like, be sure that everything's is fine with that as well. So I have 2 types of atoms defined in the simulation. Now I can put them into groups. And again, I can, instead of like, what the purpose of this is I can apply different fixes and computes to groups as well, because that's what like, the calculations act upon it as well. And plus it makes the name a little bit more clear. So now instead of like, instead of having to remember that like, type 1 atoms are hydrogen and type 2 atoms of oxygen, I can just say like, hydrogen and oxygen. And like, the union between hydrogen and oxygen is like, the water group. That's like, what all water is as well. So yes, this neighbor modify command, this is for, when I have an interaction between atoms in a particular simulation, how the simulation is progressing, I have like, a particular cutoff as to like, how many neighbors each atom has. And I need to be able to check to see like, how far are my neighbors moving away from each other as time progresses. Because if like, say at one time step, I'm like, extremely close to one atom, and then at a later time step of like, like a million times far away, I know that something incorrect happened. I know that my energy probably isn't to be conserved, so that will this cause lamps to like, shut down with like, an error. But since I'm have pretty safe settings where I'm checking I'm checking all the time, every single time step, I'm only going to see like, very minute changes between each frame of the atom as they move along. So nothing should be, so I should be able to catch any error that happens that will show like, it's something unphysical happening as well. It's setting up the initial simulation. I got the time step, which is just going to be like 1 femtosecond. It'll be like 1 depending on whatever units that you utilize in the simulation. Not an issue. Neighbor size 2. That's 2 angstroms. So I'm going to check to see each atom's going to have a radius of 2 angstroms around to see all right, how many neighbors I have within that area to see all right, I'm just going to partition off the simulation into those 2 angstrom boxes. From there, now I have this huge post-processing section, which is going to see. These are going to be all the data that I'm going to actually get from the simulation as I'm going and progressing forward. You can see that I have a lot of stuff from here. A lot of it comes from the thermodynamic output. If I can kind of flip back to let's see, the thermostat command right here. Again, these are all pretty much different types. Most of them are energy parameters. Most of them go to potential energy as well, but these are all just the kind of parameters I'm kind of checking just to make sure that my energy is being conserved. So if I flip back to here, that again is pretty much the same for all these types. I'm just going to go through one example right now, which is the compute for water. So I got a compute. The name of the compute is called T-Watt. It's acting on the water group, and the type of compute is a temp compute. So pretty much I'm computing the temperature of water. And from there, I'm going to apply a fix utilizing that compute. So I have a fix. I call it temperature water. It acts on the water group. And the type of fix it is the average for time. So it's going to output it's going to output a particular value every so often. How I have it framed right here is that every 100 time steps, I'm going to take a value. I'm going to do that 10 times. I'm going to output the average of those 10 values on the 1,000th time step. And the T watt, that's the compute I'm using. So that's the compute I want to put out every 1,000 time steps, which is the temperature of the water group as well. And then I'm going to output into a file called average temperature water.sh. So that's the file that I'm actually going to utilize and do computations on. And it's pretty much the same going down for all these other computers for the pressure, the kinetic energy, potential energy, the volume, all these information that I have right here is pretty much the same as we're going forward. Something that's slightly different down here is the compute for chunking. There's another section on that. This is for calculating the dipole moment of water molecules. I won't go too into depth to that, but it's pretty much the same premise, but I need to call it in a slightly different way in order to get the dipole moment of each individual water molecule, so then I can average that together in order to calculate the dipole moment of the system as well. But that's for a later video. And I have this commented out right here, but this right here is a dump fix, and what this does is it's going to output the pretty much just create a movie file for create a movie file for the simulation that I'm running through. So pretty much I have a dump file called test. It's going to take all the atoms in the simulation. It's going to look at each atom, going to take all its coordinate information, output it every 1,000 time steps, and output into a file called system.lamps.strj. I don't believe this is the only file type that's use that you can put a movie file into, but I know it's compatible with Obito, which allows me to kind of output a movie or do some other calculations with it as well. But that's pretty much this is just going to output the video file that I need from the simulation. When I'm kind of doing first benchmarking with the system, just trying to make sure that everything's fine, I might just reduce the number of time steps down to 1, so that when I run it on my local computer, I can kind of see to make sure that, all right, is the simulation looking how I want it to look? And if it looks the way I want it to look, then all right, we're fine. But if I know that I'm think that my simulation is only it's supposed to be a particular density, but I have a lot of extra empty space, I know that something's wrong, so I can kind of visualize it. So pretty much it's just a sanity check to make sure that what I'm seeing and what the computer's seeing are the same exact thing. So let me just put this back to 1,000, bang, comment this back out. Again, add a modifying sort. So again, I'm just going to be looking for, again, making sure that I'm every, those 2 angstroms bin size that I have, I'm just going to be checking every single time so I have to make sure that I'm not that my neighbors haven't gone too far away from each other, because if that happens, then I'm going to have an error and the simulation is going to crash. Thermal style, custom, I'm going to output particular thermodynamic properties. I output a bunch of thermodynamic properties in this file right now, in this first part up here. So, but the difference is that I'm outputting this instantaneously as opposed to doing some averaging. If I had the average values down to say just 1, 1, and 1. Those would be instantaneous. And if I had everything down to that, it would be able to check to see that if what I'm outputting here, when I'm outputting the file, should be one and the same. So then again, another sanity check. But again, why I want to just average this out up here so I can actually kind of like, get some, so that my file will be of a manageable size. I can do more stuff with it and be accurate with it. This right here, while I'm outputting it to the screen, so I can kind of see, like, how's it progressing. This things seem to make sense. If I completely out, does it look like my averages actually work out? It's again more troubleshooting to make sure that figure out like where the problem is in case something like goes wrong. So yes, thermostyle of thermal 1000. I'm gonna print that thermodynamic information every 1000 time step. So instead of doing it every single time step, which would cause the screen to be full with a bunch of information all the time, I'm only gonna output it every 1000 time steps. Looks like I have this. Looks like I had this twice right here, so this is kind of a redundant command. It's not necessary, so that's just kind of I need to kind of get rid of that as well. So again, it probably won't give you an error, but as you can see, the script isn't it works, but it isn't perfect. So there's definitely rooms for improvement as working from this. It might not be the most lean thing that we have, but it'll work for our purposes. In the restart file, every 50,000 time steps, I'm going to output a restart file, so that in case my simulation crashes for whatever reason, or if I run into a time limit on the supercomputer, I want to be able to pick up right where I left off. Velocity water create. So from now on the velocity on the water group, I'm going to create a velocity or pretty much a temperature, because temperature is based on the velocity of the water of the atoms and the water molecules themselves. I'm just going to make sure that the temperature start off with something reasonable, like at room temperature right now, because I believe this is 25 degrees Celsius. The constraint that I'm applying to the water group in order to make them rigid is the shake command. If I go back to the LAMMPS documentation, you'll end up doing this a lot when you're doing molecular dynamics. If I can just, where is it? Yeah, right here. That again, you can kind of look through here to see what you have. The two main things are the shake algorithm versus the rattle algorithm, and pretty much depending on what you're benchmarking will kind of dictate your choice into this. But if you're trying to make your own water model, you can kind of look through here to see why would I choose one over the other, what's the difference, the main difference between the two. But yeah, going back to here, I have this algorithm, then I run for 0. So this is just for me just to kind of make sure that the temperature of each water molecule in the simulation is at that temperature that I chose, which is 298 degrees Kelvin. Then I unfix it. Yes, the unfixing and fixing. So before, all the fixes that I had beforehand are going to be going throughout the simulation until the simulation ends, or until I have an unfix command. So if I wrote unfix for everything, if after one time step I ran that, it would all end. But since I want the information from the entire simulation from start to finish, I'm going to leave those on. I'm not going to unfix those. The reason I unfix the constraint commands because based on how because LAMMPS gives a good amount of information as to how I'm supposed to run a simulation. The what is it, the rattle algorithm, the shake algorithm that I have here is supposed to stop after it's supposed to be last command I run. So if I'm gonna pick up and start again, I need to call it again and then not fix it as well. But moving on down here, then I'm going to again have another fix, water NVE. So that's going to be an NVE ensemble, which is constant number of atoms, volume, and energy. And I'm also going to call a thermostat, a Langevin thermostat to it. So the combination of the Langevin thermostat and the NVE ensemble that actually results in, I believe, Brownian motion of the water molecules as well. So if you're trying to do a particular model that involves Brownian motion, this is the way you would call it. But since I'm just really trying to get the temperature of the thermostat correct, the temperature of the water molecules correct from here, and I'm going to run this for 100,000 time steps, but I'm actually going to increase my temperature from 298 to 373 because the temperature that I want to look at is actually the boiling point of water. And then again, I kind of do the same thing with unfixed particular fixes, then kind of call it again. Pretty much the same block of information from here, but instead of ramping up temperature, I'm going to maintain the temperature at 373K for 100,000 time steps. So this is to make sure that my temperature's kind of been equally rated out for a good amount of time. Then I unfix it again, and then the last thing I'm going to do is actually go utilize an NPT ensemble, which is constant number of atoms, pressure, and temperature. And I'm going to have the temperature be at again boiling point, and also I'm going to have the pressure be at 1 atmosphere. ISO, that means that the simulation domain is going to expand and contract all at the same time. That one dimension is going to move and the other dimension is going to be stacked. It's all going to compress and expand at the same rate. I'm going to run that all for a total of, I believe, 6 million time steps, which is 6 nanoseconds. And yes, the MPT ensemble is pretty indicative of actual experiment, which is which if I could actually look at a steam table, pressure and temperature I could look at, and then I'm supposed to get particular values for density, enthalpy vaporization that I can compare to make sure I compare that to actual steam tables or the benchmarking that I'm doing to make sure that what I'm doing is correct, and then I can do my other experiments onto it to add an electric field or other or other ions into it to see is that what I'm going to do. So this is all just for benchmarking, and that's pretty much kind of the basic structure of this file for benchmarking water. So yes, that's all I have.